So it's a pleasure to introduce Luca Marchetti, who will be telling us about cosmic emergence and quantum gravity, and then Fabio Mele, is that right? Sorry, yeah. Is going to be commenting. So go ahead and take it away.
Thank you. And thanks to all the organizers for having me and putting together this super interesting meeting. So yeah, I'm going to talk about cosmic emergence and quantum gravity, and my talk is going to be divided into two parts. In the first part, I will discuss the difficulties that we're actually facing when trying to understand the cosmic emergence process in quantum gravity, and I will also suggest some methods in which we can actually address these difficulties, at least in an approximate sense. In the second part of my talk instead, I will give you some concrete examples of how we can actually implement these suggestions within a specific approach to quantum gravity. And I will also offer 3 examples of cosmological phenomena that can be understood as emergent from a quantum gravity perspective. Which way I have to pull it? Okay. Okay. All right. So let's start from the more general discussion, and let's ask ourselves what are the difficulties that we're facing when trying to go from the far left side of this diagram to the right side of this diagram. So on the left, we have our microscopic quantum gravity description, which I'm assuming to be described by a theory which is background independent, non-perturbative, and whose fundamental degrees of freedom are, in principle, not directly related to the usual space-time quantities that we're used to. So we can call these fundamental degrees of freedom pre-geometric degrees of freedom. Now, if we look at the right side, which is cosmology, the first thing that we want to do if we want to extract some cosmological physics is that we need to obtain geometries which are smooth from our pre-geometric degrees of freedom. And this is a non-trivial task, which is known as the continuum limit problem in quantum gravity. But smooth geometries are not what cosmology is all about, because cosmological geometries are also almost spatially homogeneous and isotropic and time-dependent. But then, how do we define something that is spatially homogeneous and isotropic, or almost so, and time-dependent in a context which is completely background independent, so where there's no external notion of space and time, and which is also pre-geometric, so where any space-time notion has disappeared completely. So this is, we can call this the localization problem in quantum gravity. Now, there are ways to address these problems. If we want to take the perspective of condensed matter physics, we can try to address the problem of continuum limit by constructing an effective theory, which is continuum, through an appropriate Coarse-Graining. And we can try and address the problem of localization drawing inspiration from general relativity, because, as I mentioned, it's a problem that is intrinsically related to the background independence of our theory, which is a feature that is also present in GR. And the way to address that in GR, that we know it works, is to implement a relational strategy. So try and localize physical and internal degrees of freedom with respect to other physical and internal degrees of freedom. Now, implementing these strategies in quantum gravity is extremely complicated, both for conceptual and technical reasons. So let me spend some time trying to explain what are these difficulties. So, okay, we want to study the continuum limit problem in quantum gravity. What does this mean physically? It means that we should be able to take into account a large number of dynamical degrees of freedom, or quantum gravitational degrees of freedom in our theory. So in practice, this means that we should be able to compute the full partition function of the theory. If we're able to do that, we should also be able to draw a diagram like the one that you see over there. Where we should be able also to identify different phases of our quantum gravity theory, potentially some that have no continuum interpretation, which we can call pre-geometric phases, and some that actually have this continuum interpretation, and if we're doing a good job, we should hope to find also a phase that coincides with GR in a certain limit. So, okay, so we just need to compute the partition function of the theory. But this is complicated, because the best way we know how to compute the partition function in general is through the normalization group procedure. And that's the most effective way of doing so. But doing that in quantum field theory on space-time and doing that in quantum gravity are two entirely different things, both for conceptual and technical reasons again. So starting from the conceptual problems, one of the main points of the renormalization group strategy, one of the main ingredients, is the introduction of an energy scale, which defines the flow from the IR to the UV, and vice versa. So what does this energy scale is in a context where there's no, where there's complete background independence, there are no external structures, there's not even necessarily an asymptotic structure that you can anchor to in order to define any notion of time and hence any notion of energy scale. So this means that we should be able to describe this renormalization group flow in terms of internal variables. But this means that UV and IR have very different meanings in quantum gravity than they do in standard quantum field theory and spacetime. So this is mostly a conceptual problem, but there are also technical problems. And one of the most important ones is that the reason why the renormalization group strategy is so efficient in standard quantum field theory is because we're always trying to describe systems whose symmetries we know very well. And these symmetries are very, very constraining. They constrain the theory space so much that basically we're actually able to do some computations. Symmetries of quantum gravity models, on the other hand, are very hard to classify, and they're much more complicated than the usual ones that we're used to. So this means that we have very little control over the quantum gravity theory space. So should we lose any hope of actually computing the full partition function? Well, I would argue that we should try to look for approximate methods. And the reason for this is that approximate methods would allow us to have more mathematical control, which we desperately need. And more mathematical control could help us to gain more physical insights, which is also something that we desperately need, which in turn could help us better our approximations and create a positive feedback loop. And this is in fact what happened historically, even for the development of the renormalization group procedure, where the Landau-Ginzburg mean field strategy was the first step towards developing the full renormalization group strategy. And the mean field approximation is something that I'm going to discuss. It's going to become relevant also in the following. It's exactly equivalent to what the Landau-Ginzburg idea was. And it's essentially a saddle point approximation of the full partition function. So you're not actually computing the full functional integral. What you're doing is just compute a saddle point of that. Yeah, so that will become relevant in a moment. So now let me talk a little bit about the localization problem. So as I said, the problem of localization is already there in classical GR. It's due mainly to the background independence of the theory, and we know how to address this problem through the relational strategy. And this is quite well understood from a classical perspective, but much less from a quantum perspective. So let me review very briefly what the classical story looks like. So the best way we know, well, a very efficient way of implementing the relational strategy is through the construction of relational observables. So what are relational observables? Let's consider a system which is a time reparameterization invariant, so just a simple system. So then we take two phase space functions. One we call it f, and the other one is this t. And t is the quantity that we want to use as a relational clock. So we want it to have non-zero Poisson brackets with our generator of our time reparameterization symmetry. Then you can combine these two quantities to construct a relational extension of your small f, which we call capital F, which essentially encodes the value of small f when your clock t reads a certain value tau. And evolution with respect to tau is now relational, so it tells you exactly the value of f when your other physical quantity reads a certain value. So the thing is that these relational observables are very complicated functions in general, and we have applications almost only for very, very simple systems. Now, when you turn on quantum effects, the situation becomes way worse because, as you could expect, the quantization process and the implementation of the relational strategy in general do not commute. So you could do two things. You could decide to quantize first, which is the Dirac approach, which is great because then you get to a perspective neutral framework where you can actually choose at the quantum level different physical frames, at least in principle. But then to do so, you have to actually solve some quantum constraints, which means being able to actually obtain the physical Hilbert space of the theory. And this is something that is extremely complicated to do, at least in quantum general relativity. The other way around would be to instead implement the relational strategy first and then quantize. The huge advantage of doing this is that you don't have any quantum constraint to solve because you're already quantizing all gauging variant degrees of freedom. The disadvantage of that is that it's not perspective neutral. You're already quantizing within a frame, so it's really hard to ask any questions about covariance or quantum covariance for that matter, which are questions that you could ask in principle within the Dirac frame. But still, even in this case, this is too complicated to implement in most of the cases. And if you can believe it, the situation becomes even worse when you deal with emergent quantum gravity theories, where your fundamental degrees of freedom, as we said before, are only weakly related to space-time quantities, and these space-time quantities are expected to emerge only when you take a continuum limit, for instance, in terms of collective observables or cosine states, as we said before. And the reason is clear. It's because the quantities whose evolution we would like to describe relation, and we actually know how to describe relation from our continuum intuition, are now the result of a prior coarse graining or fundamental degrees of freedom. So you see already that the two issues that I mentioned before are deeply intertwined because, as you see here, our relational intuition is based on the continuum limit, so it means that in order to implement the relational strategy as we know it, we need to address the continuum limit as well, the continuum limit problem as well. On the other hand, as I said before, to address the problem of continuum limit, the most effective way would be to implement a renormalization group strategy. But to do that, we need to face the problem of a scale. And naturally, one will look for relational scales, which is something that forces us to address the relational problem, the problem of localization. So yeah, these two problems are related one with another. But again, we could use effective approaches, which allow us to have more mathematical control and get physical insights. And most importantly, they are relevant for observative purposes. So okay, we've seen that these two problems are somehow interrelated one with another. This, of course, complicates everything. But it's also a good thing because it means that if we're able to maybe address one of the two, we could have a chance to also address the other one. So this is what I want to show you, that through some choice of appropriate states, we can actually effectively approach both these problems and go towards the cosmology side from our fundamental theory. And as the approach of quantum gravity that I'm going to follow, this is going to be the group field theory approach to quantum gravity, which I'm going to introduce very, very briefly. I will try to be not too technical, but if any of you have any questions about it, please feel free to stop me at any time. So what are group field theories? Well, group field theories are quantum field theories, but not on spacetime, but of spacetime. So they take very seriously the idea of a microscopic structure of spacetime, but they're still full quantum field theories, so you still have access to all the powerful field theoretic methods that you want, Fock space description, renormalization group, and so on and so forth. So what are the fundamental quantities theories? These are atoms of three-dimensional quantum space, so you can see them as tetrahedra, but these tetrahedra are decorated with data which are associated to the values that fields would take when discretized over the tetrahedron. So for instance, you would have gravitational fields, which once discretized over the tetrahedron essentially give you the shape of the tetrahedron. And then you would have matter fields. In this case, I'm going to focus only on scalar fields for simplicity. So what happens when you act with your field creation operator on the Fock vacuum of the theory is that you create one of these quantum tetrahedra, which is decorated with these discretized field values, which enter as arguments of the field itself. So this shows that the field is not really a function on space-time, but actually on discrete field space. So what about the quantum gravity processes? Quantum gravity processes can be represented in terms of Feynman diagram, as in standard quantum field theories. And it turns out that this is an important point, that these Feynman diagrams are dual to four-dimensional triangulated pseudomanifolds. So what happens when you write the partition function of this theory? If you write this partition function of this theory by summing over all possible Feynman diagrams, what you're doing is you're essentially summing over all possible triangulated spacetimes. And because these boundary states essentially carry with them information about discretized fields, the amplitudes that would enter this partition function would also carry these labels which represent these discretized fields. So if you choose these amplitudes correctly, the partition function of this theory is nothing but a discrete matter gravity path integral. So one good thing about these theories is that they share a lot of physical insights coming from other approaches to quantum gravity. For instance, for those of you that are more familiar with quantum gravity, they surely have noticed that, the kind of fundamental quanta that we have in these theories are essentially open spin network vertices. And the kind of construction that I outlined here is very similar to the construction that is done in spin-foam models, simplicial gravity path integrals, CDTs, and so on, while group field theories are technically just a generalization of tensor models. So a good thing about this is that there are some insights that are shared within these theories and other approaches to quantum gravity. So these are a good paradigmatic example in which we can actually study some of these complicated problems. Okay, so as I promised, I want to show you that we can address these two problems by choosing appropriate states. And if we want to address the continuum problem, as we said, we need to include a large number of quanta. So if we want to look at states that are going to describe our continuum geometries, we want to look at states that can accommodate such a large number of quanta. The simplest kind of such states are coherent states. Where you see here, this is the coherent wave function, or the condensate wave function, as it's normally called in group field theory literature. And it's going to depend on the same kind of data that enter in the group field. Here, we're going to have our gravitational field and some arbitrary number of masses scalar fields. And what's important is that the dynamics of this condensate wave function, which is in a sense a macroscopic variable as standard in condensed matter physics, is determined when interactions are small through this mean field approximation. So, and this is really the simplest form of coarse graining in the sense that I mentioned before. What we're doing is just computing the full partition function, but through a subtle point approximation. This is really the simplest thing that we can do at the level of coarse graining. But these states are collective, so they would allow us also to implement a formal relationality, at least in an effective sense, at the level of averages of observables. So suppose that we have our scalar fields here, that we have these 4 scalar fields that we can use that represent a physical frame. Then the only thing that we need to do in order to construct our effective relational observables is to assume that the condensate wave function factorizes into a peaking function, which is fixed and peaks on some arbitrary values of our physical reference frame, and a reduced condensate wave function, which is dynamically determined through these mean field equations. So what you do when you take expectation values of general delocalized observables in your quantum gravity theory, they become localized in virtue of the local properties of the states. So they become functionals of the reduced wave function evaluated at a certain point x mu. And this x mu carries physical value because it's in fact the expectation value of your physical reference frame. So these are really relational observables in an average sense. An important example of these observables is the number operator. We just count how many number of group field theory quanta we have in our system. And this is an example of the expectation value of the number operator on these kind of states, where you see it's localized with respect to the field data, or completely delocalized with respect to the gravitational data. And it counts all the number of quanta which share this kind of value for the physical frame. Okay, so with this construction, we could go towards the macroscopic description and cosmology. And here, let me give you 3 examples of emergent cosmological phenomena from the perspective of quantum gravity. So the first is going to be about the singularity resolution and the classical limit. So we want to look at homogeneous isotropic cosmology. And these are conditions, of course, these are macroscopic conditions from the perspective of quantum gravity. So these are conditions that we're imposing at the level of the condensate wave function. So we require the condensate wave function to only depend on some minimally coupled masses and free clock field. Isotropy is a little bit more tricky to visualize, but the thing is that the domain of the condensate wave function carries essentially the same kind of data that the tetrahedron would. So projecting down isotropic modes means essentially saying that the data that will represent the faces of the tetrahedron are all the same. The areas of this imaginary tetrahedron would all be the same. And this can be captured by saying that when you go to representation space instead of group space, all these representation labels all collapse into a single variable. For those of you that are more familiar with spinfold models, these variables would be belonging to alpha integers for EPRL-like models or real values for Barrett-Crane-like models. Another important assumption, and I will come to this in a moment, is that we neglect the group field theory interactions. If you do this, the dynamics of the condensate wave function is extremely simple, and it's this one. And once you solve for the condensate wave function, you can actually study how the volume of the universe itself evolves. Because this is the expectation value of the universe, and you see it depends clearly on the modulus of the condensate wave function. And this was the same kind of dependence that we found here. So the picture here physically is very clear. The number of quanta increase, and therefore also the volume increases. Okay. And so you can explicitly compute the dynamics of the volume, and these are the awful equations that you get. But there are two interesting limits in which these equations look a little bit nicer. The first is the classical limit. So you look at a regime where this modulus of the condensate wave function is very large, and dynamically this corresponds to late times. And in this regime, by assuming that one of these microscopic variables is associated to the gravitational coupling, and it's only mildly dependent on your group theoretic labels, what you find is that the dynamics is that of a flat Filmer-Robertson-Walker universe. Not only that, you can also compute quantum fluctuations of all of your observables, so clock and geometric variables, and show that they're all suppressed. And they're suppressed for a very simple reason from a condensed matter perspective. It's exactly because this limit when rho is large and when the volume is large, it's also a limit in which the number of quanta is large. So the number of quanta is essentially suppressing all these quantum fluctuations. So what happens if you go instead at earlier times? At earlier times, you can show that the singularity is resolved into non-zero volume bounds for a large range of initial conditions. But we should keep in mind that this singularity resolution is actually only an average singularity resolution. So if the number of quanta gets small, close to the bounds, this means that we could have large quantum effect both on geometric and clock variables. So we could have large quantum fluctuations on the clock, meaning that these equations for the expectation value of the clock would not be reliable anymore to describe the physics of the system. Or we could have large quantum fluctuations on the clock. And in that case, what happens is that this equation here will not capture anymore the relevant physics. So x mu would not represent the physics of the real physical frame. So if we follow x mu in our evolution, we're not actually following the real clock evolution. So we're kind of losing track of time in that sense because of quantum effects. So the effective approach that we're using would break down. But it should be said that if you, for some range of initial conditions, so if you set this number of quanta not to be too small around the bounds, none of these problems arise, obviously. Okay, another example that I want to discuss is cosmic acceleration from quantum gravity interactions. So let me go back to the interactions that we neglected so far. So there are two types of interactions that I will very briefly discuss here. The first are the tensor interactions. Tensor interactions are highly symmetric in the sense that there's, just to visualize them, in the sense that we have an identical power of the field, the complex conjugate of the field, the group field here, the group field and the group field itself. And so just to define a little bit the notation here, one important feature of this group field theory is that their interactions are combinatorially non-local. So the pattern of combinatorial contraction between the powers of the group field that appear in these interaction terms is actually characterized by a graph, and this is what this pattern of contraction is encoded into this kernel here. This is just a minor thing, but At any rate, these tensor interactions are highly symmetric. Those are the ones that are studied actually in renormalization, exactly because of their symmetric properties. And what these interactions look like after you go to mean field is that these interactions only depend on the modulus after you isotropize. On the other hand, if you look at cellular interactions, these do not share the same kind of asymmetry that we saw before, but they admit a more clear geometric interpretation because they actually represent the gluing of these fundamental tetrahedra into four-dimensional cells of spacetime. So they have a more clear geometric interpretation and can be connected more easily to spinfold models or simplicial gravity path integrals and so on. In this case, when you go to mean field and isotropize, you get a dependence both on modulus and phase. So why am I bothering you with all this? Because there's some interesting physics that come out from these different kinds of interactions. So if you look at modulus interactions and include a dominant and a subdominant spin or representation label, you get a universe which is effectively dominated by an emergent phantom dark energy. And here I'm emphasizing not pathologic because the usual problem with phantom dark energy is that you're actually putting a field there that represents phantom dark energy, and that has negative kinetic energy, a lot of instabilities. But none of that is there here because this is just an emergent feature of the universe. It looks like an emergent phantom dark energy, but it's not that we're putting an emergent phantom dark energy there. If you look instead at phase interactions, and let me tell you, first of all, these results are preliminary. It seems that we're able to actually find a slow roll phase, which is characterized by a long-lasting quasi-de Sitter phase, which naturally breaks down and produces fast oscillations, which essentially average out these interaction terms here. So we're back to the standard dynamics where there's only a matter, so clock field dominated universe. So despite of whether or not this picture will be confirmed once we go more into details of all this, the general picture that seems to emerge is that we can actually recover some cosmic acceleration as a result of purely introducing back interactions in our quantum gravity model. The last example of emergence in cosmology from quantum gravity is going to be about inhomogeneities. So let's define a very simple cosmological-like inhomogeneous system, which is made of our four minimally coupled masses and free reference fields, so the ones that are going to make our physical reference frame, and one matter field, which is expected to be dominating the energy momentum budget of the universe, and which is only slightly relationally homogeneous with respect to our Roth fields. So this is really a simple cosmology-like system with just mass scalar fields. Now, how do we describe this system at the quantum level? So we should expect that we have to go beyond condensates, or the simple states that I showed you before, for two reasons. The first is that in order to capture completely the causal properties of our physical reference frames, it's important to have both time-like and space-like tetrahedra. So tetrahedra of different kinds with different causal properties. But this is more of a technical point. More physical point is that we do expect from our quantum gravity insights that non-trivial geometries with non-trivial curvature and so on are associated with quantum entanglement within the fundamental quantum gravity theory. And this is the reason why we not only include this term here, which is just a space-like condensate, or this one, which is a time-like condensate, but we also include these terms here, which encode correlations between our fundamental group field theory quantum, both between the space-like and time-like sector and within the space-like and time-like sectors. So what happens is that you can study you can show that the perturbations in matter and curvature-like isotropic variables emerge exactly from this kind of correlations that we're assuming here, just for simplicity, to be two-body relational nearest neighbor correlations. And you can study the dynamics of these things. And the dynamics is really the GR one, which is the left-hand side, plus some quantum gravity corrections here at the right-hand side, which are suppressed for scales which are below the Planck mass. And so there's a remarkable agreement with GR larger scales, but there are these quantum gravity corrections that are there. And you can see this in this plot here, where we plotted both the curvature perturbation for group field theory and GR in the top diagram, and it's exactly superimposed, so you can't see anything with naked eye. But if you look at the difference between the two, you can see that there's some shift between the two. And this is for a mode which is 10 to the 2 times the Planck mass. So the differences are really, really small. But despite these corrections, which could lead to interesting phenomenological implications, what these results suggest is that really this kind of idea should be there. So the idea that inhomogeneities emerge from quantum entanglement is something that makes sense, and it could be actually the main mechanism behind the generation of the primordial inhomogeneities in our universe. All right, so I'll just summarize the story that I told so far. So we've discussed some generic difficulties that one faces when trying to go from a microscopic quantum gravity description to a macroscopic cosmological one. We mentioned the continuum limit problem and the localization problem. We addressed the continuum limit problem via the simplest form of cross-grading through mean-field equations, and the localization problem through the implementation of a relational strategy in an effective sense. And this was achieved by looking at specific kind of states. And through all this construction, we were able to actually look at cosmology with different lenses. So we were able to find singularity resolution, quantum geometric acceleration, and the classical limits as emergent phenomena from quantum gravity, as well as primordial inhomogeneities associated to quantum entanglement within the fundamental quantum gravity theory. And whose dynamics is characterized by Trans-Planckian corrections with respect to the classical one. So of course, there's a lot more work to do. We need to include more matter components so that these results could be actually compared with actual cosmological physics. And we would like to extend this to vector and tensor modes, study the primordial power spectrum, study the classicalization problem at the level of inhomogeneities. And these are just, these are problems that can be addressed within this framework. More complicated questions, which I would like to put out for the discussion session, is can we actually construct relational observables completely within the fundamental quantum gravity theory? How do we define a full renormalization group analysis which is relational within the fundamental quantum gravity theory? And of course, these are challenging goals, so every bit of input is important, especially if it comes from different perspectives. That's why I thought that was the perfect occasion to do this. Okay, that's all. Thank you.
And it's Fabio. I welcome you to comment.
Right. Thanks, Luca, for the nice talk. So my comments are kind of like divided in two main parts, and then I have some open questions that maybe can be just for open discussions. So the first one is more about the general strategy, and maybe I can just do the first, then you can comment on it, and then we continue. So the first one is, as far as I understand the GFT program, I may be oversimplifying it, but let's say the strategy schematically is like, as you said, I have to address these three problems together: continuum, classical limit, and the relational localization. And you achieve that by the continuum is implemented by a collective behavior of your space-time that you are regarding as a quantum many-body systems. The classicality aspect is captured by the states and observables you are looking at. And then the relational notion of time is in terms of, for instance, the clock field you are using. Any particular states you are considering are condensate states. But as you say, GFT is also related to other approaches. So I was wondering how much of this strategy. So first of all, is there any fundamental reasons why you look at condensate and you apply this strategy beside of the intuition from condensed matter? And if yes, how much of this strategy can be useful as a lesson for other approaches to quantum cosmology and quantum gravity?
Okay. So regarding condensates themselves, as I said, I would like to see them as a first step towards the direction of trying to address the continuum limit problem. But as we saw in the inhomogeneity part of the story, these are not condensate states. There's entanglement here, so these are something different. So, but condensates are the starting point. So the idea is to look at collective states. And this is one of the important principles that I think comes out of this whole story. So I would say that there are some important principles that come out from this kind of story. One of them is the fact that we should look at collective states. The other one is that we should look at the relational implementation of our dynamics. And the third one is that we should, if we want to really implement non-trivial geometries or study non-trivial geometries, we should look really into quantum entanglement. Now, what is nice about this construction is that we have concrete examples in which these general principles actually happen, and we have some control over them, so we can try to look at the regions in which this kind of principles should be implemented, regions in which these kind of principles and approximations are not reliable anymore. So this is useful. And related to if we can actually implement the same ideas to other approaches, that's one of the things that I would be very much interested in doing. So, because so as I said before, the good thing about group field theories is that they share a lot of physical insights with other approaches to quantum gravity. Maybe the math is a little bit different. So, of course, one would like to construct a map that sends you, for instance, from group field theories to quantum gravity, so you're actually able to map one-to-one whatever you're doing in one theory to another one. And that would be ideal and it would be amazing. But maybe it's too complicated to achieve in general. Maybe that's not actually the case. Maybe the theories somehow are different in some aspects, and we should be able to quantify what are these differences. But at any rate, what I think that it's important, rather than focusing on the detailed mathematical construction, is to actually extract the core of the physics that is in there and express it in a language that could be also understandable in other approaches to quantum gravity and implemented in those approaches to quantum gravity. And I feel like, again, group field theories are kind of good at this because the language that we're using is similarly shared with other approaches to quantum gravity. So if we're able to reformulate everything in a way that is accessible to other approaches to quantum gravity, that's the goal, I think.
And actually, yeah, following up on, because yeah, you said it's important actually to track the validity of the approximation. So this, yeah, naturally brings me to the second part, which I think it's also connected to Sean's talk before lunch, which is about, yeah, the size of the system. So here you actually get FRW cosmology, which then means that it's spatially non-compact, right?
Yeah.
So coming, for instance, I work mainly on the canonical side, and from that point of view, actually there, the size of the system does matter, namely that indeed it's true that classically there is a symmetry under the rescaling of the size of the finite volume you use to regularize your spatial slice. But physically speaking, that has the interpretation of the sides over which you are imposing homogeneity. And that's actually physically relevant for tracking the validity of the homogeneous approximation, so of the mini superspace approximation. And at the quantum level reflects actually, I think, as you said also in your model, with how quantum fluctuation may or may not be relevant in going from early times to late times. But I was wondering how this discussion enters in your setting. So how do you track the validity of the homogeneous approximation? And that's probably links also with the second part of like, how do you introduce inhomogeneities? And there is also the discussion of combining these two to be compatible with, for instance, the BKL scenario when you approach the would-be singularity. So how does that fit in your picture?
Yeah, right. So to answer this question, one would have to, I believe, work within fully homogeneous models plus anisotropies, which we didn't do here, but there are independent studies on anisotropies that show that like anisotropies kind of are washed away at late times. So you should be able, in principle, to do exactly what you do from the canonical perspective or standard cosmological perspective. In this scenario as well, when you start from the fully homogeneous system, with one important difference, which is that inhomogeneities here are defined with respect to your physical reference system. So even if you project down somehow or average out all modes and you project into the k=0 mode, so the homogeneous mode, that doesn't wash away the contribution of your physical reference frame to the Hubble constant. They will enter into the energy density of the universe anyway, because they're there. So that's an important difference, and it could lead to maybe some differences. I don't know. That's something that it should be done. None of that has been done. So far, the analysis of the mini superspace has been done as a first step. Then we started looking at the inhomogeneity, and this is just 2 months old work. So there's very little work on that, but it's something that it would be really interesting to do. And again, I think that the procedure could be developed exactly in the same way, but with important physical difference that you would still have to deal with your physical reference frame, that it's always there.
Sorry, but what is the... so here, as far as I understand, the homogeneity is implemented by the dependence on only one scalar field.
Right.
And isotropy is implemented by the fact that everything depends on one single group representation.
Yeah, in this case, yeah.
How does that connect with the idea that, for instance, we have, even classically, of looking at homogeneous cosmology as a mode expansion and then truncating just to the homogeneous k=0 mode?
Yeah, so you will start from something like this, where you have your full system, which is fully homogeneous.
Mm-hmm.
Then you would integrate over a large area, and that's what you would project onto the k=0 mode in a relational sense, though. So not with respect to physical coordinates, but with respect to your physical reference frame. So even if you do that, you would have the contribution of the physical reference frame in your homogeneous energy density, because they're essentially, they give you a contribution to the energy momentum tensor, which is constant. So it stays there, whatever you're going to do, even if you project down to the k=0 mode.
Do the inhomogeneities somehow tells you that to neglect them and keeping the homogeneous approximation, you will need to rescale the size of your system or not?
That's a good question.
So, okay,
yeah,
that's not addressed.
I have no idea. Yeah. Something that we need to look at very, very carefully, especially because inhomogeneities here are encoded in these entanglement functions, not in these terms are instead the homogeneous ones. So the question is, how does this entanglement then back react so that you essentially create just these functions here plus some contribution from entanglement? That, I don't know, it's something that needs to be done. But yeah, the framework in which you could do it seems to be straightforward. The results, I don't know.
Go ahead, Francesca.
Thank you. It's a follow-up because I do have problem to grasp this idea that inhomogeneities are equal to quantum entanglement, because when you do cosmology, you do quantum field theory on curve background. So it's true that there is a relation between inhomogeneities and entanglement and entanglement entropy, but they are not the same thing. And let me clarify. So, of course, if you have a certain geometry, and on this geometry you have quantum fluctuations, these fluctuations are the one that brings the idea that we have is that this will give rise to the inhomogeneities. So then you want to study correlations between given by associated with these fluctuations, and entanglement give a bound on the correlations. But I mean, so it's relevant to study entanglement, but it's different with respect to correlations. Also, if you constrain yourself only to entanglement, well, you are focusing on a subclass of correlations. You're not considering all the correlations that creates inhomogeneities. So I want to understand better why you have this statement there.
Right. So the idea is that you get these functions here, these delta phi and delta psi and delta xi, are essentially squeezing operator. They produce entanglement between two quanta of the group field. So in principle, this is something that I believe we haven't done that, but I think that you should be able to encode higher order correlations as well, 3-body, 4-body, M-body correlations as well. So it's just not But the simplest thing to do was just to truncate at second order, so just squeezing and size the system that comes out of that. I don't know if that answers your question. So maybe when you...
Yeah, I mean, so do you agree that this doesn't encompass all...
No, this doesn't encompass all possible correlations within your quantum gravity system.
And all the inhomogeneities that you want to describe. Sorry? And doesn't encompass all the inhomogeneities that you may have in cosmology.
Oh, yeah, I mean, yes.
So you cannot really make an estimation of... so it's hard for me to see how you go from here to a quantification of inhomogeneities in cosmology.
I mean, it depends. No, well, how you go from here to here, this is just a matter of saying, okay, these correlations are relationally inhomogeneous, slightly relationally inhomogeneous, and then from the operators that I showed you before, you take an expectation value on these states here, and you get this kind of inhomogeneities and homogeneous parts. So that's the kind of that's the mathematical explanation. But what you're saying is that I think what I think you're saying is that in principle, all kinds of correlations should contribute to this kind of inhomogeneities, right? And yeah, that I agree that in principle that's the case. But the hope here is that there's some kind of hierarchy between correlations. If there's no hierarchy, then you need to go fully non-perturbative, sum everything, and that's going to be really, really hard to do. But the fact that already at the lowest order we can recover GR plus something else, I think it's a good indication that we are on the right direction. Maybe these terms here will get corrected somehow, but maybe you can either these terms should get corrected in a non-perturbative way, then the result may change substantially. But if they get corrected in a perturbative way, then we might be on the right track.
Sean also had a question.
Yeah, it's just like a follow-up to this, like a slightly different tact on the issue. Where does the scale come from? So like inhomogeneities have a particular scale, but presumably that's a lot different from whatever scales you have in the full quantum gravity theory. So the question is like, where, I mean, I guess you're not saying that you're getting empirically adequate results right now, but how could you imagine the right number coming out of this?
So that's a question of, you mean about the primordial power spectrum? This is just dynamics. There's no statement here about the primordial power spectrum. This is just the dynamics that these perturbations satisfy. So there are two ways in which you can study the primordial power spectrum, right? You could study these modified dynamics, quantize it, and look for a primordial power spectrum corrected by these dynamics. That's one way. The other way, if you want to work fully within the quantum gravity theory, is to get to the modified counterpart of the Bunch-Davies vacuum from within the quantum gravity theory. But that means being able to recover not only classical gravity, but it means being able to recover quantum field theory and occur space-time from quantum gravity. It's a much more complicated problem, in my opinion. Yeah.
Yes, Nick?
There was a step in sort of the story that's probably a couple of slides before this that I didn't sort of understand. Yes, sorry.
Yes, so this is just a kind of comprehension. So it's the bit where you talked, this relational peaking. I thought I was going to get what was happening, but then I'm kind of confused why the number operator would have something to do with localization. What does localization kind of, talk me through here, if you don't mind. What does localization kind of really mean here, and why is the number operator an example of that? Because it's sort of intuitively, it isn't obviously.
So the number operator is probably the worst example I could make, but it was an important one, so I had to make it at a certain point in the talk. Because the number operator has no classical counterpart, right? So the intuition that we have from classical GR is rather something like this. So geometry evaluated a certain value or physical clock. This is how a relational observable looks like. And you can do this kind of procedure with any kind of operator that you have from within your quantum gravity theory. In particular, we can think again of a geometric observable like the volume operator. So let's focus on the volume operator here. So you take an expectation value of the volume operator, which in general would be very similar to this number operator here. So you see there would be an integration over the group variables, over the scalar fields, over everything. But here we would have eigenvalues of the volume operator instead of 1, which is the number operator, right? So when you do that, when you take the expectation value of this observable on your peak states, what you're getting is essentially, because of the peaking, that this becomes just a functional of the reduced wave function evaluated at the point of peaking. So from something that was completely delocalized, you get something that is localized because you're taking expectation values on something that is localized. And then the question is, what is the physical interpretation of this variable here? In principle, none, but then you compute the expectation value of the physical frame, and you realize that it's actually the expectation value of the physical frame. So what you realize that what you actually computed was the volume average at a certain value of the average clock or physical frame. In that sense, is an average definition or effective definition of the relational observable. Does that make sense?
So it is localization in, there's a point in this talking where it sounds like it's going to be a localization in the spectrum of the operator, so that we have sort of peaked values, but you do really mean...
No.
So that's the volume sort of at around that point,
exactly,
something like that. So it is localization.
That's exactly right, yes.
Okay.
Around that point, not in the space-time, but in the space of physical fields, in the physical manifold. Space-time is not in
the point picture. In the x mu, in the chi mu frame.
Exactly.
Yeah.
Yes.
Yeah. Okay. Thank you.
Other questions for Luca? And I can't see everyone clearly on it. Okay. Fabio has another one. Yeah.
I mean, these are not really related to the previous discussion, but was wondering two things. So first, as far as I can see, you're matching with the classical FRW equations requires that Newton constant comes to be dependent on the parameters of your model. Does it mean that you expect some rounding of G?
Yeah, so we have some suggestions on that. Accidental suggestions, I should say, because we were looking for something else and then we realized this. So we were trying to couple a scalar field with a potential, and trying to couple a scalar field with a potential forces you to, for technical reasons, forces you to look again into the interactions of the group field theory model. So you have to turn them on. So then we looked at the late time Friedman dynamics of this kind of group field theory model with interactions so that you would also have this scalar field potential. And the only way in which we could match classical Friedman dynamics is if the gravitational constant runs in the exact same way as you would expect by naive dimensional analysis. And this is also the same kind of running that has been found in asymptotic safety and stuff like that. What's interesting, well, it's two things. The first is that this kind of running kind of makes sense because we found it exactly when we turned on interactions. Without interactions, you're not going to see anything running. So that made sense. The other thing that makes sense, I think, is that the running is in a relational sense. So the running is with respect to the relational time. And this is the reason why I'm pointing this out. Because I think that the theory itself is suggesting, maybe you should look into the renormalization group from a relational perspective. So yeah, but that's just an effective running. It's just a naive dimension of the coupling. You're not getting any anomalous dimension, so it really means that we're just working 3 level. There's nothing particularly exciting going on there at the quantum level. So maybe if we manage to do that at the full quantum level, we could actually see some anomalous dimensions popping on and stuff like that.
But then if it is a relational running, I presume that the way in which things run will depend on the frame you're choosing.
Yeah, maybe there's a covariance of the full renormalization group. I have no idea. It's just I'm putting them out because I think it's a cool idea, but I haven't done that. So we're actually trying to think about it within the context of asymptotic safety, because there they naturally fix this gauge so that you're actually are working essentially in harmonic gauge. And if you have some scalar fields which are massive free and without any potential, so these fields satisfy harmonic conditions. So you could try to adapt your gauge to your dynamical fields and try to recast that in a relational way. That's something that we're trying to look into. But yeah, it's really early stage.
Yeah, okay, no, that's actually interesting because yeah, fixing gauges is actually related to choosing frames.
Yeah.
So that could be interesting. Okay.
I think I had a much cruder version of the same question, which is when you started, you explained why the typical ways of thinking about renormalization group analysis wouldn't carry over to quantum gravity, and how you thought that the problems of continuum limit and relational localization would help each other. But I didn't get a full sense of now, if you go back to the initial statements about how it is that we have challenges with renormalization group analysis, how does the relational RG approach answer those, and to what extent does it answer those?
Yeah, so it's gonna take ages before I get there. All right, okay. So yeah, this is so it's not gonna solve all the problems, but it might solve some of the problems. Like this scale problem, which is a big one, both for quantum gravity and even in continuum theories, like in asymptotic safety, they also have difficulties in understanding the physical scale. So if you're somehow able to characterize this scale as something that comes out of a specific choice for the physical reference frame, then this scale is physical, and you can perhaps study the running of observables in a relational way. So the running with respect to your physical relational frame. And in that sense, you still wouldn't have any external kind of time as you would have in quantum field theory of spacetime, but you could have an internal kind of time, which is defined in a very clear physical way. So you know that time corresponds to choosing a physical reference frame, which is given by that, and that field. In that sense, that's what I meant. So it wouldn't solve all the problems, but I think it will clarify a little bit what's going on with this big problem here.
And do you have, in terms of the second problem, the control over the quantum gravity theory space, is there some way in which you're addressing that one as well, or is that's more challenging?
That's challenging.
Yeah, okay.
That's honestly challenging. What people are doing, at least in the context of group field theories, is looking at simple things like these tensor interactions. Mm-hmm. They're already really complicated because you still have to deal with the fact that these interactions are not local. Mm-hmm. So the normalization properties are different from the standard ones that are used in quantum field theories. Mm-hmm. But yeah, there's very, very little work, at least from the perspective of non-perturbative on these kind of models, which instead are those that we know how to connect better to geometric models, or to spin-foam models or Luca.
Great, Sean, go ahead.
Yeah, so I just have a question about the logic, and this could just be a very ignorant question, so maybe you can set me straight. But so you're calling these things condensates, right? And I guess the different in condensed matter, when you talk about like condensates, you normally have the phase diagram, right? So you have an understanding of the RG flow of the theory, and then you can show within that there's a phase that is a condensate phase. And that justifies then using those condensates to do mean field approximation. So in this case, I guess you still don't have that phase diagram.
No, not the full phase diagram.
Right. So you're guessing, I guess, that there will be a phase like this that will have the properties.
Yeah, that's true. In a sense, you're guessing that there is a phase which is characterized by this kind of collective behavior. Uh-huh. One thing that we did prove, though, was that this kind of mean field approximation is very, very, very reliable, much more than in standard quantum field theory or in standard Landau-Gies group analysis. And the reason for that is that there's this is not a field theory on like R⁴. It's a field theory on a group domain. And the gravitational part of the group domain is the Lorentz group, so it's a cell to C. Now, the Lorentz group has an hyperbolic structure, And because of that hyperbolic structure, the impact of quantum fluctuations over the mean field, so if you write your partition function as mean field plus Gaussian fluctuations, and you ask yourself, okay, when do these Gaussian fluctuations become important and break down my old mean field theory? Well, normally there's a critical dimension in standard quantum field theory. If beyond the critical dimension, your mean field approximation is not reliable, and you have to look at full renormalization group to actually do the computations. Here, this doesn't happen. No matter what is the dimension, because of this hyperbolicity of the Lorentz group, essentially there's an exponential suppression of these Gaussian terms, these Gaussian additional fluctuations, which never even reach the point of breaking down your mean field approximation.
So the hyperbolicity is helping you finally.
Sorry?
The hyperbolicity is helping. Finally.
It's helping, yeah.
It's usually a pain in the butt.
It's surprisingly enough, it's helping.
But then I have just like, I mean, do you even know that these states are saddle point approximations of the classical action that you start with?
Well, you actually solve the mean field equation.
Okay,
so you know that that's a solution.
But then, okay, so just to go back, just to finish the question, was the logic was kind of like, we're going to use these approximations to get information about the phase diagram.
Right.
But it seems like to do the approximation at all, you need to make assumptions about it. So,
no, I would still stand with what I said, in the sense that, like, the thing that I mentioned before about the running of G, the relational running of G, that's an insight on how you should implement the normalization group procedure, and we found it in the mean field approximation. So yeah, I would still say that it's a starting point that will give us some insights on how to actually do the full thing or do it better. Even these beyond mean field computations that we did with Gaussian fluctuations, they are also characterizing kind of the phase diagram around the mean field, the broken region, if you want. So it's not the full phase diagram, but you're kind of looking at a region around it.
okay, no, thanks. Yeah.
Fabio.
Just want to make a comment on what you just said. And I mean, correct me, Luca, if what I say has no sense, but I was just thinking, I mean, maybe not from the full theory phase diagram point of view, but I guess in condensed matter, one other way to think about the formation of condensate is by looking at longer range correlations as order parameter for it. Maybe not in the full GFT setting, but for instance, already, yeah, Luca here is just considering the 2 points correlations, but maybe if you modify the states suitably to have longer range interactions, that could be a way to probably get as a process the condensate. I'm guessing.
Yeah, I mean, yeah, that could be an option.
Go ahead, Nick.
So it's another kind of question of the first kind as well. Let's try to make sure. Could you just go over the bit about the singularity resolution? Yeah, how the... So what's actually happening, kind of? So this is at the early universe kind of bounce, right? So what does it bounce into on the? So just.
It's exactly the universe that is bouncing back. So you can see that is the volume, and what happens is that so this is the Hubble parameter. What happens is the Hubble parameter gets to 0 at a certain point. So you're actually getting a bounce. And this bounce happens when the volume is not 0. So you're just going back to what was happening before. So the universe grows again.
So is it symmetrical? I mean, like reverse symmetrical about the bounce?
Yeah,
exactly,
yeah.
right? So, okay. So you don't end up in a sort of non-geometric phase or something?
No. Well, again, this is a question of quantum fluctuations. If the number of quanta is large here, then you could be, this whole description could not be valid anymore. Then you don't know even if there's a bounce or something like that. It could even be that you're actually getting out of this mean field description, so or average description rather. And in that case, maybe something else happens. You get to pre-geometric phase, and that's something.
Just a clarification on this point, because you said it depends on the number of quanta.
Yes.
But I thought you always need a large number of quanta to talk about a condensate state.
No, you can have condensates with very small number of quanta. They do that in quantum
Like
optics
3.
as well. Yeah.
Okay.
Yeah, with average number of quanta. Like the condensate itself includes. Well, let me maybe that wasn't clear enough. So if you look at this includes an infinite superposition of quanta, right? And so in principle, you can have an arbitrary number of quanta, but the average number of quanta can be as small or as large as you like.
Any other questions or comments? Okay, well, please join me in thanking Luca for his talk.